We all know how heat works in real life scenarios, but how does it work on a more molecular level? When energy is added into a system, the increased energy has effect on the molecules within the system. The molecules become more energized and they begin to move around more. As they bump into each other, they begin to expand and take up more space. An example would be water boiling and turning from a liquid into a gas. In other cases, energy or heat is taken away from the system. When this happens, the molecules have less energy and they begin to condense together because they're not moving around as frequently. In this experiment, I use a balloon filled with air and a candle. This will demonstrate how heat transfer works. With nothing in the balloon, the heat from the candle will cause the latex to melt, and then the balloon will pop. In this trial, I'll take a little bit of water and put it at the bottom of the balloon. This will delay the process of the balloon popping because the heat will transfer through the rubber latex into the water and cause it to boil. But there won't be enough water in there to keep the latex from burning and popping the balloon once again. In this final trial, I put a lot of water at the bottom of the balloon. This will cause the heat from the candle to transfer through the latex into the water. The water will then begin to boil from the heat of the flame, but the latex of the balloon will not burn. Therefore, the balloon will not pop. All that's left on the bottom is a black soot residue from the burning candle. In this experiment, Taylor demonstrates thermal conduction. Thermal conduction is when heat is transferred from one substance to another. To do this, he takes a flame from the lighter and holds it under a piece of paper. The result is that the paper burns in seconds due to the heat. Next, he takes another piece of paper and wraps it tightly around a copper pipe and holds it against the flame. The result is that the paper this time does not combust and has no evidence of any damage from the heat. The reason for this is that metal is a better conductor, and then the heat passes through the paper into the metal, where it is spread out, causing the paper to be exposed to less heat than the first time. In this experiment, Taylor shows how two different substances will have two separate specific heats. Specific heat is a quantity of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. He compares water with a specific heat of 4.19 joules per kilogram times Celsius and vegetable oil, which has a specific heat of 1.67 joules per kilogram times Celsius. This means that, in theory, water takes a significantly less amount of time to increase its temperature. Therefore, when boiling the two liquids, the water should boil more quickly. As you can see, the water takes less time to boil than the vegetable oil, proving that in fact, two different substances will have two separate specific heats. Just to be sure that you could see that the water was boiling, Taylor thought it would be a good idea to put one piece of pasta in each pot to demonstrate that one is boiling and one is just frying a piece of pasta. In this experiment, Ashley uses a teapot to show how heat can be used to do work. Energy transferred as heat turns water into steam. Energy from the steam does work against the force exerted by air outside of the balloon. This causes a balloon to blow up due to the steam pressing on it from the inside of the can.
What is a heat engine? Well, a heat engine is something that uses heat to do work. And a diagram is a pretty good way to explain this. A heat engine needs to have two things: a hot reservoir at a certain hot temperature, and it also needs to have a cold reservoir at a certain cold temperature. Now, by reservoir, I mean that it's so big that it never changes temperature. And an engine is between the two of these reservoirs. And the engine takes heat from the hot reservoir and brings it into the engine. And then it produces work. But there's not an equal amount of work to the energy going in. So we don't have 100% efficiency. So also heat must be wasted and dumped into the cold reservoir, and heat always must be dumped when you're using an engine. Now, efficiency is the net work over the energy in, or energy in minus energy out over energy in. So our equation is 1 minus the energy out over the energy in. We also have what are called non-engines, and non-engines are almost the opposite of engines. An air conditioner is a pretty good example. It also has a hot reservoir at a certain hot temperature and a cold reservoir at a certain cold temperature. And what it does is it takes the hot air from the cold reservoir and brings it into the air conditioner. And then it dumps the hot air into the hot reservoir. But heat can't just flow freely, so we know that work has to be present to make the heat flow. And, well, you can consider the cold reservoir is inside of your house, and the hot reservoir is outside of your house.